When a program runs, we often focus on the instructions, but instructions alone are not enough. Execution requires temporary memory. As a processor performs a task, it creates intermediate values. Numbers are calculated. Results are passed between steps. Temporary information appears and disappears constantly. That information must live somewhere. So whenever a task begins executing, the system creates a small workspace in memory. This workspace holds everything the task needs while it runs. And when the task finishes, the workspace disappears. This is an important behavior in software execution. Temporary memory does not exist all the time. It only exists when a task is running. When execution begins, the system creates a new region of memory for that task. Inside that region, the system stores temporary values, intermediate results, parameters, execution state, everything the task needs to complete its work. Once execution finishes, that memory is no longer needed, so the system removes it. This constant cycle creates memory. Run task, remove memory, happens millions of times every second in modern software. Execution rarely happens as a single isolated task. Instead, tasks frequently start other tasks. For example, one task begins executing, then during execution, it calls another task. That second task now needs its own temporary workspace. So the system creates another memory region for the new task. Now two temporary workspaces exist, one for the original task, one for the second task. This layer structure is how complex software manages operations happening within a single program execution. Each new task adds another layer of temporary memory. Imagine the memory structure like stack layers. The first task starts and receives memory. Then it calls another task. A new layer appears. If that task calls another task, another layer appears. Execution grows this layer structure as tasks begin, and as tasks finish, the layers disappear in reverse order. The newest layer always belongs to the newest task, and once that task finishes, its memory disappears immediately. This predictable pattern is essential to understanding execution behavior. Whenever a new task begins, execution shifts to that task. The processor now focuses on the newest layer. This means the most recently started task always runs first. When it completes, execution returns to the task beneath it. This pattern repeats continuously. New task begins, memory appears. Task finishes, memory disappears. This system keeps execution organized and predictable. Others' temporary data and programs would become very chaotic. One of the defining characteristics of temporary memory is that it is automatic. Developers do not manually create this workspace. The system manages it for you. When a task begins, memory appears. When the task ends, memory disappears. This automatic behavior keeps programs efficient. Memory is only used when it is needed, and it disappears as soon as the task finishes. This constant creation and removal of temporary memory is one of the most fundamental mechanisms in computing. This layered memory model solves several problems. First, it isolates tasks. Each task gets its own workspace, preventing interference. Second, it organizes execution. The newest task always runs first, creating a predictable structure. Third, it simplifies cleanup. When a task ends, the system removes its memory automatically. This design makes it possible for complex programs to run thousands of nested tasks safely and efficiently. Whenever a task runs, temporary memory appears. When tasks call other tasks, new memory layers appear. When tasks finish, their memory disappears. Execution constantly builds and removes these memory layers. This system keeps tasks isolated, organized, and efficient. Later, when we introduce actual programming languages, you will see that this layered temporary memory structure has a specific name. But the concept is what matters. Execution always brings memory with it.